In section 3.3, we're going to learn about the addition rule. So you can recall that the multiplication rule we used to find the probability of two events that occurred in a sequence, so event A and then event B happening. The addition rule is used to find the probability that at least one of two events will occur. So the probability that A occurs or B occurs or both. In order to use the addition rule, you need to understand when two events are mutually exclusive. Two events are mutually exclusive when A and B cannot occur at the same time. That is, A and B have no outcomes in common. I have a couple of pictures here to illustrate the difference. So in the first sample space, we have event A and we have event B. And you can see that between them, there's this area of overlap that they have in common. Those are shared outcomes that represent the probability of both A and B happening at the same time. So in this instance, because they do have shared outcomes, A and B are not mutually exclusive. To be mutually exclusive, they need to look like the second picture here, where A has all of its own outcomes, B has its own outcomes, and they don't share any in common. So you want to make sure that you're keeping these concepts straight. For the multiplication rule, we need to know if events are dependent or independent. For the addition rule, we need to know if the events are mutually exclusive. So here's how that works. I modified example 1 slightly in number 3. It says determine whether the events are mutually exclusive. Explain your reasoning. So event A is rolling a 3 on a die. Event B is rolling a 4 on a die. If I list the possible outcomes for event A, if I want to roll a 3, there's only one way to do that, which is for the 3 to be facing up. If I want to roll a 4, the only way that that can occur, the only outcome that's possible, is if the 4 is facing up. So, since these two events, when I look at their sample spaces, do not have any outcomes in common, these events are mutually exclusive. In number 2, it's event A is randomly selecting a male student, event B is randomly selecting a nursing major. So suppose I have a classroom, and in that classroom, I have some male students. So, for example, I'm just going to choose names like maybe Chris or Deshaun, etc. And now suppose I list the students in my class who are nursing majors, and it might be Tina and maybe Deshaun and maybe Ella. So, is it possible for a student in my class to be both a male student and a nursing major? It is. So, because that is a possibility, event A and event B can, in fact, have outcomes in common. So, these events are not mutually exclusive. In the last situation here, event A is randomly selecting a Bills fan, and event B is randomly selecting a Sabres fan. So, again, what we need to ask ourselves is in the sample space of Bills fans, my brother in particular is a Bills fan. My sister is also a Bills fan. In terms of Sabres fans, my brother is, and actually, so am I, even though I don't know why. But anyhow, so when I look at the sample spaces here, is it possible that I could choose a person who is both a Bills fan and a Sabres fan? Yes, because they have the common outcome here. My brother is, in fact, a fan of both. Since A and B may possibly have outcomes in common, a person who is a fan of the Sabres and the Bills, these events are not mutually exclusive. All right, now we're ready to look at the addition rule. So the addition rule for the probability of A or B happening, either this or that happens. In order to calculate it, it's given by the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Because essentially, if you take the probability of A happening and the probability of B happening and they have something in common, you'll count it twice by including one outcome in both of those probabilities. So by subtracting that common probability once, you've taken care of that overcounting issue. If your events are mutually exclusive, if they have nothing in common, well, that would mean the probability of A and B is nothing. And so you can simplify this first formula by basically just ignoring this last term, and you can see you can just take the probability of A plus the probability of B. And the simplified rule here for mutually exclusive events, you can use that for 2 events, 3 events, 4 events, as many as you need to calculate. All right, I modified example 2 to add an extra part. But number 1 says you select a card from a standard deck of 52 playing cards. Find the probability that the card is a 4 or an ace. So I'm going to let event A be choosing a 4. And I'm going to let my event B be choosing an ace. And before I use the formula, I need to decide, are these mutually exclusive? Well, to choose a 4 from a deck of cards, I could choose, the 4 of hearts, the 4 of clubs, the 4 of spades, and the 4 of diamonds. If I want to choose an ace, there are 4 different ways to do that. Again, all the same suits, but now choosing an ace. So when I'm finished, if you look back at my sample spaces, do I have any outcomes that are identical to both sample spaces? And the answer is no, there's nothing in common here. So because of that, these are known as mutually exclusive events. We're not going to double count anything. So therefore, if I want the probability of A or B, I will just take the probability A and add probability B. The probability of getting a 4, there are 4 outcomes out of 52 total, plus choosing an ace has 4 outcomes out of 52 cards total. And here's where it's helpful if you don't simplify these fractions. Very often when you're using the addition rule, when you add fractions, you have to have a common denominator. So it's better to avoid simplifying anything and just leave it the way that it is. So I would add my numerators. 4 plus 4 is 8. Remember, when you add, you just keep the common denominator. The answer is going to be 8 over 52. That does reduce to 2 over 13. And if you pick up a calculator, that's going to be approximately 0.154. In number 2, I'm still choosing a card, but I'm going to find the probability that the card is a 4. So there's my event A. Or my event B, choosing a red card. You can see I've written out the sample spaces for both events. Event A was the same as before, 4 possibilities. Choosing a red card, well, all the hearts and all the diamonds are red. So I've listed each card individually after that suit. So ace, 2, 3, 4, etc. So now what I want to look for is if I have any shared outcomes, an outcome that exists in both event A and event B. And certainly you can see I do have a 4 of hearts in each one. I also have a 4 of diamonds in each one. So therefore, because they share an outcome, these events are not mutually exclusive. So when I calculate the probability of event A or B, I now need to use the version of the formula that subtracts the probability of that common event. So the probability of event A happening, there are 4 ways that can happen out of 52 cards. The probability of event B happening, the red cards are half of the deck. So if you count all of these possibilities up, there will be 26 of them. But you can see if I do that, I've counted 4 of hearts and 4 of diamonds in event A. I've also counted it in event B. So I've double counted it. So I need to subtract the probability of A and B both occurring. So the probability of having a 4 and a red card, there are 2 outcomes that fit that description of being both 4 and red. So I'm going to subtract off 2 out of 52. Work across your numerators. 4 plus 26 is 30. Take away 2 is 28 out of 52, which does reduce to 7 over 13. And using a calculator, we get the decimal 0.538. So there's decent chances that you will get a 4 or a red card, and that's simply because there are so many red cards. All right, the last example, you roll a die. Find the probability of rolling a number less than 3, so that's my first event, or event B, rolling an odd number. So assuming that this is a 6-sided die, rolling a number less than 3 would include the outcomes of I could get a 1, I could get a 2. I wouldn't include 3 because that would be equal to 3, not less than 3. So 1 and 2 are the only sides that are less than 3. If I'm rolling a 6-sided die, the odd numbers that appear on a die are the numbers 1, 3, and 5. Now we check to see if we have any outcomes in common, which we do. There's a 1 on both lists. So these events are not mutually exclusive. And again, that means I need to do that extra subtraction step so that I don't double count the probability of one happening. So probability of A or B, probability of getting a number less than 3, there were 2 outcomes out of 6 on the die, plus the probability of event B, there are 3 outcomes out of 6 on a die. There's only one outcome in their shared sample space. There's only one outcome that appears in both A and B, so I'll subtract 1. I work across my numerators. 2 plus 3 is 5. Take away 1 is 4. Out of, keep the same denominator. That, of course, reduces to 2/3, which is approximately 0.667. So again, because this is above 50%, this is a somewhat likely event to occur.